All right, continuing. Calculus with parametric equations. So we're going to start with one idea. The idea is, if I were to give you a curve like this, true or false, that curve is a function. Okay, now let's say that I wanted to find the slope of this curve at a certain point, like P. So our goal right now is to find the slope of a curve at some point. Now, back from your calculus days, what is the slope of a curve at a point? What's that called? Did you all pass calculus some more? It's a derivative, that's right. So we're going to be talking about derivatives, but we've got to find a way to go about doing this. You see, here's the thing. If that's not a function, firstly, we probably can't go about it the same way that we've been doing this. When we took derivatives, the idea of a derivative was this. You find a derivative of a function in terms of one variable, right? And then we say, okay, well, now plug in like the independent variable x, and it will give you the slope of the curve at a point. If you're not with me, the whole idea was you can't take a derivative of something that's not a function, because when you try to plug in one number, it's going to give you out 1, 2, 3 answers. That means if we were somehow to find the derivative in terms of x alone, if I plug in the value where p is, the x value of where p is, it would not give me the slope of p. At least it would give me 1, 2, 3 different slopes there. Does that make sense? So we can't even find it because it's not even defined as a function. So here's our idea. Do you guys see the point I'm trying to make as far as that goes? If we don't have a function, we can't do it the same way we did in terms of one variable alone. Well, because we can define these curves as parametric equations rather than functions, maybe we'll try a different idea with this. The different idea is, what if we can just cut a part of this and say, well, you know what? That's not a function, but if I cut a piece around p, let's cut a piece so that it becomes a function. So that's our idea. So we're going to cut the curve so that the interval around p is a function. Well, how are we going to do that? Okay, I'll start this. I can go down as far as I want as long as where I make the cut, I have a function. You guys remember the vertical line test? Use the vertical line test to help you here. So I'll go down here and go, all right, well, maybe I stop. I wouldn't want to go down to here because I'm going to fail the vertical line test there. Does that make sense? So I'm going to stop so that I find some point, doesn't matter, as long as it's just around p, you don't have to go that far, where that I don't go any further because I want to maintain my functionality. I want to maintain my function here of this little piece around p. Does that make sense? Now, of course, if I want to find the derivative or the slope at p, I'm probably not going to cut it right here. I need to include that point p in this little miniature function that we have. Quick head nod if you're okay with that so far. Okay, so now you tell me where to stop. Should I stop here?
No.
Okay, I've got to go past the p, correct? So stop me when I get to a point here.
No.
Oh, you missed
You
it.
went too
Oh, you guys are
fast.
too slow. I thought you had it, but now, I mean, I'm just a little. Okay, where do I stop? Do I want to go way up here?
No.
Before it curves.
Back.
There.
you go.
Anywhere in here. Here, whatever. Anywhere in here before it starts to double back on itself. Would you agree that between the two purple dots we have a function?
Yes.
And this is the idea. We're going to cut this so that we get a function around our point P. Now, let's suppose also, because this is not a function, we can define it parametrically. Let's define this x equals f of t and y equals g of t. Now, this should be nothing new for us. We've seen parametric equations before. You all right with that one? If x is a function of t, and if y is a function of t, then we're going to have our inputs and our outputs for these 2 points. Let's say that t starts at A and t ends at B. So t is part of the interval a to b. If I plug in t equals a, then my input here, do you guys remember our points x, y? You don't have to write this down, just watch. For x, y, we really don't get x and y. We really get f of a and g of a. Do you guys remember that? Because if I were to plug in a, I'd have, well, f of a gives me my x. If I plug in a, g of a gives me my y. So for each point, I'm going to have an f of a and a g of a, an f of b and a g of b. If this is f of a, tell me what, let's see, f of a, tell me what this is. Good. Are you all okay that that's g of a? Remember, our points are f of a, g of a, because we're getting them by plugging in t. In our case, t goes from a to b. So it says, all right, start with a. You know how you're going to find that point? You're going to plug in a here. It's going to give you the x. Boom. You're going to plug in a here. It's going to give you the y. Boom. Therefore, for our first point, we have f of a, comma, g of a. And that's exactly what this says. Show of hands if you feel okay with that one. Okay, let's keep on moving then. What's this going to be, an f or a g?
F of
G. This one.
F of B.
F of what?
B.
Very good. Therefore, this is going to be
G of
You guys notice, I hope, that x's are f, the function f. Y's are the function g. You still okay with this so far? All right. So we got this function. It goes from this point to this point, or this point to this point. It does not really matter. We're just cutting this so that it's a function. That way we can do our calculus with it. Right now what we're going to do is we're going to go through the process of finding a derivative, finding the slope of a curve at a point. That's what a derivative is, with just this section of the function. So for a small section of the curve, right here, for a small section of that, we could define y as a function of x. I'm going to write that down so you guys have some notes later. So for the small section of the curve, in other words, our function, we could define y as a function of x. Let me do like a 10-second recap to make sure you guys are all with me. So we go, is this whole thing a function? Heck no. So if I want to find the slope of a curve at a point where we don't have a function, I'm going to have to cut it. I'm going to have to cut part of this thing. Cut it here, cut it here. Therefore, this piece is a function. If I erased everything else, would you agree that that little piece would define a function?
Mm-hmm.
The function would go from t equals a to t equals b. That's where we go. F of a, f of b, g of b to f of b, f of a, g of a to f of b. That's hard to say. F of b, g of b. That's where we go. Boom, right there. That's a function. Now, if I erase everything else and have this little function, I could define y as a function of x. Does that make sense? If I do that, y would be equal to a function, I'm going to use capital F, a function of x. Are you okay with that? That that's allowed to do? That I could, for that little curve, that little piece, y could equal some function in terms of x. Show of hands if you understand that concept. Okay, we're going to do some razzle-dazzle, some mathematical magic up here. Here's what we're going to do. We're going to do a whole bunch of substitutions. So now think of this. You agree with this, right? You just raised your hands and you did the verbal contract that you agreed with that. So now, ergo, we can continue. Here's the deal. We already took for granted that x equals f of t and y equals g of t. That's literally where we got this stuff from, right? We defined a parametric equation for this curve. Then we said, all right, now cut it. Okay, if this is a parametric equation, this has to happen. Now, our little curve goes from a to b. No problem, from a to b. We can define that as y in terms of x. Well, y is a function of x. But now, because it came from our parametric equation, it still has to fit the rules. It's got to fit those pieces. Well, And then instead of this, what could I write instead of my y? Look over there. What could I write instead of my y? Let's do a substitution. Remember, y still has to fit the rules. Y still has to be g of t. Big F, that's all good. That's why I'm using big F, because what could I write instead of x? F of t. Little f of t. That's why I use the big F of t to define my function of x, because I'm talking about a different function here. So, whole thing over again, here we go. You got something that's not a function, it's a parametric equation, therefore we define it as such. We say let's cut it. Let's cut it from t equals a to b so that we get a function there. Any function that we have, any small piece, we could define y equals a function of x. We're going to do that. I'm using big F of x because I've already defined another function f. Do you guys see the point here? Okay, well if that's the case, then I go, cool. This function, even though it is y in terms of x, it still has to fit the rules of my parametric equation from whence it came. Therefore, y can equal g of t, no problem. X can equal f of t, and right here, this is where we're going to start our derivative. So let's do a derivative. Remember that we can do a derivative of both sides, yeah? So if I do a derivative, check this out. The derivative of g of t is simply g prime of t. Well, that was easy. Let's take it to, remember, we're doing derivative of both sides. So if I take a derivative of g, I get g prime of t. In fact, if you want me to show the notation, I can do that for you. Take a derivative. Yeah, you know what? I don't want to do it because I'm going to show it to you differently in just a moment. Yeah. Okay. I'm using two different Leibniz and Newton notation, so it looks a little funky. But if I do this, the derivative of g with respect to t is g prime of t. Do you see the notation at work here? Are you okay with it? On the other side, well, look at, okay, now you know enough about calculus to understand from calculus 1 exactly what's going on here. Something special is happening here. What is it? It's a chain rule. That's right. Chain rule works this way. Chain rule says that you take the derivative of the outside function and you leave the inside function alone, and then you do what? Very good. We multiply by the derivative of the inside. I want to make sure that y'all are okay with the chain rule. Do you guys see the chain rule at work? This is chain rule. Hey, derivative of g of t? No problem, g prime t. Derivative of f, big F of t? Well, it's a derivative of big F. Leave the inside alone, times the derivative of the inside. Show of hands, feel okay with it. Now, we're going to do another, I told you we're doing lots of substitutions. Are you okay making it down from here to here, and now from here to here? Yes, no? Okay, well notice how with f of t is the same thing as x, correct? I'm going to resubstitute there. So I'm going to leave g prime of t equals, the big F stays, the prime stays, everybody, what does f of t become? X. Times little f prime of t. If it looks like, oh my gosh, what are we doing? We're almost done. I want you to see it. Check it out. Look, 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 look. Do you understand that we called this little piece big F of x? Do you get it? So this piece, we said, hey, that's a function, big F, a function of x. Not a problem. Do you see the derivative of big F of x somewhere in here? Yeah. Then what we have in here, it's mixed in, it's the derivative of this little piece. We said this is big F of x. We now found a derivative, oh, look at that, it's right there. We found a derivative of that little piece. This stands for the slope of a curve at a point. It is the derivative. Let's solve for it. If we should just divide by little f prime of t on both sides, we get f, big F prime of x equals g prime of t over f prime of t. If you go, what in the world does that mean to me? Well, it should mean something kind of nice. It says basically this. It's really, really easy to take a derivative of a parametric equation. You think of just the curve. Part of the curve is a function. We've just proven, do you guys see why we've proven the derivative here? This is big f of x, that's what it is. We've proven that the derivative of big f of x is this relationship. That means that to find the derivative of a parametric equation, it's really easy. Look what it does. Do you see where g prime of t is? You're going to be given that, right? G prime of t is right here. Take a derivative of this one, put it over the derivative of this one, and you're done. That's it. It's not even a quotient rule. It's easier than that. It's just boom over boom. That's it. Isn't that kind of nice? And did you follow this proof? Kind of nice, right? Of course, we have different notation. This would be the Newtonian notation. If you want it a little differently, dy dx, you understand that that's also derivative, equals dy dt over dx dt. Do you see that these say the same thing? G of t is y. Therefore, g prime of t is dy dt. That's the idea. Does that make sense? In fact, you know what? You can do a really simple proof here if you want to. It's even easier. You don't need to write this down, but you can if you want. If I took dy dx and I multiplied by 1 over dt, I get dy dt over dx dt. It's that simple. What's nice about parametric equations is that y and x are not functions of each other in parametric equations. They're both functions of t, which means that this really says this: the derivative of y over the derivative of x, because they're not functions of each other. The functions of t. It's easy. Hey, that's a derivative of y, that's a derivative of x. Done. That's all you got to do here. Show of hands if you feel okay with the idea. Do you want to do some examples real fast just to illustrate this? Any questions at all? Do you understand the idea of cutting the function? Do you understand why we have to do that? Okay, so we're cutting the curve. We make a little function. Then we kind of use some razzle-dazzle and go, oh, okay, function's this, derivative of the function, after working all this stuff out, is this, the derivative of the y over the derivative of the x in terms of t. Let's do an example to flesh this idea out. So, what I want to do, it's a longer problem. We're going to go through it quickly, but there's a lot of stuff to it. None of it's hard, all right? It's all first semester calculus ideas. But it's based on parametric equations. So what I want to do is find the equation of the tangent line at t equals 4. Pi over 4. Sorry, not 4. Be way outside of our domain. Here's the idea. The first thing, what type of a curve is this? We better at least know that. What type of curve is that? I don't care what it looks like. What type of a curve? Is it a function? Is it parametric? Is it polar? What is it? It's a parametric equation. So that's some sort of a parametric curve right there. The idea behind finding a tangent line is, at this curve, wherever it is, I want you to find the line that hits this curve at one point only for that area. Now please listen carefully. These aren't functions, right? They double back, they do all sorts of weird things. So this tangent is only going to be a tangent for the neighborhood. So wherever you cut your function, it's going to be a tangent for that little piece. It could very well, if my graph wraps around, it could be a tangent and hit something else. Does that make sense? So when I say tangent, it's not tangent for the entire parametric equation. It's a tangent for the neighborhood around our point, where we define our function to be. Does that make sense to you? Some of you is like zoned out. I need you to understand that, okay? You with me? So it hits our curve at one point for the point around the neighborhood where, remember how we cut our function? It'd be the tangent for that function. It could go ahead and hit the other part of it after we lose that functionality of our parametric equation. I just said a whole lot of words. Did they all make sense to you? Rewind that. So, what do we need in order to write the equation of a line? There's two things. There's only two things you need to write the equation of a line. What are they? Slope and?
Y-intercept.
Nope. Slope and? You're close. Slope and? From algebra, you need two things to write the equation of a line. Slope and a point. That's right. You need slope and a point. Do we have the slope yet? No. Do we have a point yet? No. We only have t. So let's do the point first, just for funsies. Could you find the point at t equals pi over 4? Did you get the point? How do you find the point? What is my point? I don't know. How do you find your point? What would you do? Okay, do it right now. Find the point at t equals pi over 4. Go for it, quickly, please. What do you do in order to find the point? What do you plug in and where do you plug it in? Pi over 4, and where do you plug it in? Good, so here and here, this will give you your x coordinate, this will give you your y coordinate, x and y make a point. This is the point. I'll do the hard one for you guys, okay? So tangent of pi over 4, that's 1, so I know that y equals 1. So on my point, I'm going to get something, comma, 1. Now, I left you guys with the easy one. So, secant of pi over 4, naturally, it's 2 over the square root of 2. Did you find that? Yeah, it's 2 root 2, or 2 over root 2. If you have 2 over root 2 and you rationalize this, you're going to get the square root of 2. So this is the square root of 2. Okay, I want to show of hands if you feel okay with that so far. Okay, again, the two things you need to find the equation of a line are what? Slope and a point. We have a point. So here's what this means. We're going to draw this curve. Okay, we're actually not going to draw it. But were we to draw this curve? We draw the curve. I don't know what it looks like. We're going to cut a piece around this point, square root of 2, 1, such that our piece is a function. Are you listening? The tangent will touch this parametric equation at this point and no other point for our function. It might touch the other graph when it curves around and becomes not a function. But for that little neighborhood, it's going to be tangential to this parametric equation. You with me? Now, how do you find the slope of a curve at a point? Number one thing that I taught you in Calculus 1. The slope of a curve at a point is a...
Derivative.
Can you find the derivative of this? It's easy. So the derivative, dy dx, is simply dy dt over dx dt. So in our case, dy dx equals... Can you find dy dt? If I were to write it right. I just like x's today. dy dt over dx dt. Can you find dy dt for our example? You better be able to find dy dt.
Yeah.
Do you know the derivative of tangent with respect to t? Have I lost you? I don't want to lose you. Do you get the idea of what we're trying to do here? You say, hey, you know what? If you want to find a derivative, it is not hard. Do the derivative of y. Do the derivative of x.
Squared.
Simplify them. This is your derivative. What's a derivative stand for? I know I've asked it 3 times now, but you need to know. What's a derivative stand for in terms of function?
Slope.
So this is our slope. Now, notice how it's based on the correct variable of, hey, could you find the slope at a t value?
Yes.
Then that's all it's asking you to do. So if I want to find my slope here, look at what we did. To find my point, what I do? Plug in t. Plug in t. I found my point. To find the slope, what am I going to do? Plug in t. So at pi over 4, our slope is secant of pi over 4 over tangent of pi over 4. Now, fortunately for us, we already calculated these two things for our point. So this is 1, this is root 2. So it's root 2 over 1 or the square root of 2. That's our slope. Now, from here on out, it's literally just algebra. We have a slope, not the best looking slope in the world, and we have a point. Can you use point slope to write the equation of a line?
Yes.
Lines never change in math. They're always lines. So when we have point slope formula, let's fill it in. This should be y minus what, please? Oh, come on, I need more out of you. Y minus what? What's our y?
1.
Y minus 1 equals, what's our slope?
Square root of 2.
And then x.
Take away root 2.
Can you solve that for y? First step would be to distribute. We get y minus 1 equals square root of 2x minus 2. Square root times itself gives you the radicand. If I add 1 over, y equals the square root of 2x minus 1. Hey, ladies and gentlemen, what's the slope of this line?
2.
Is that coincidence? That's where we got that from, right? That is our slope. Here's what this says. If you were to graph this parametric equation, and if you were to graph this line, yes, it's a line, what this line's going to do, it's going to hit this parametric equation at exactly the time of pi over 4 at the point square root of 2, 1, and will hit only at that point around that neighborhood for which you cut it into a function. Show of hands if you understand the idea. That's it. Do you guys see the calculus 1 at work and the algebra at work that we've been doing like our whole lives? It's kind of interesting. Are there any questions at all before we continue to the next idea?
So you don't actually have to cut a section out manually?
No.
You just, through derivations, you just find the spontaneous slope of that particular point?
What this is giving you is, it doesn't, unless you have a point where you have a horizontal tangent, which we're going to cover right now, you can cut a neighborhood so that you get a function. And that's the idea. I kind of neglected that, but the point is that with any parametric equation, unless it is exactly vertical, you could find a neighborhood that you have a function. You could get small enough. But it's microscopic, but you could get a small, teeny, little bitty function. Does that make sense? That's what it says around the neighborhood. I don't know where you're going to cut it. It could be miles. It could be nanometers. But the point is that for whatever you do, this line will intersect that parametric equation at this time, at that point, and will intersect it only once for a neighborhood around that point. Not forever, but just where it is a function. Does that make sense to you? So the equation of the tangent line is only relevant to the neighborhood where you have a function of the parametric equation. It's a lot of big words right there. You might want to think on that or watch that again. Or if you have any questions right now, I can answer them. Did that make sense, what I said? Okay. So the next couple ideas. So like I said, this is like all the calculus all at once. This is like all of semester 1 calculus on parametric equations in one lesson. Next idea. How you find horizontal and vertical tangents. That should sound familiar. Well, think of this. dy dx for a parametric equation is dy dt over dx dt. If you think back to your idea of limits and where you get vertical tangents and where you get horizontal tangents, here's where you got them, even from your pre-calculus days. Here's where you got them. You will have horizontal tangents. Tangents or asymptotes or whatever. In our case, we're going to have tangents. We're going to have horizontal tangents. Horizontal tang. I love tang. Don't you guys love tang? Or Tampico? It's about the same thing. You don't like Tampico?
I love
Oh, I was poor. I had to. I couldn't afford orange juice. Tampico.
Tampico's fine.
Anyway, what was I talking about?
Talking about tangents.
I was talking about tang, actually. I wasn't talking about tangents. Weren't you paying attention? Duh, Tambigo. Horizontal tangents. When you did limits, horizontal tangents were when basically you go to infinity and your numerator equals 0 and your denominator does not. Well, in our case then, it's going to be where dy dt equals 0. That's where we're going to get a horizontal tangent, where the numerator is 0 and the denominator is not. Where dy dt equals 0 and dx dt does not equal 0. I'm just going to abbreviate it differently so we don't get off topic here. Vertical tangents. Where do vertical tangents happen? Remember dividing by 0? You're like, oh, I can't do that. That's going to create a vertical tangent. Well, if you're talking about slopes, dividing by 0 means that you have an infinite slope, a vertical slope. That's why the derivatives are equal to 0 here. A horizontal tangent means that, well, a horizontal tangent would have a slope of 0, wouldn't it? The numerator would be 0, the denominator would not be 0. That's why we have that. For a vertical tangent, well, the numerator would be a number and the denominator would be 0. So here we say, hey, if numerator is 0 and denominator is not, it's going to be horizontal because the slope's 0. Hello? It means slope. It's derivative. Vertical tangents say, well, if this is a number and this one's 0, we're dividing a number by 0. That's a vertical asymptote in functions. That's a vertical tangent for parametric equations. So it's to say, okay, dx dt would equal 0 and dy dt would not equal 0. We're not going to cover this case in this class, but if you were to have both a case where dy dt equals 0 and dx, you might get it on your homework, but not today in class, where dy dt equals 0 and dx dt equals 0 at the same time, that could be both a horizontal and a vertical asymptote, or it could be one or the other. You'd probably explore L'Hopital's rule to deal with that, because the derivatives are all about limits. So you can explore L'Hopital's rule with that to figure out which one it is, or if it's both of them. Does that make sense to you? Okay. And in functions, it becomes a whole. In slopes, it becomes a little bit weirder of an idea. So here's the plan. We're going to do one example. We're going to find the horizontal, the vertical asymptotes, and we're going to put this stuff all together. Are you guys ready for it? I was going to ask if you had questions, but I nailed this one, so we're good. That was a joke. Anyway. Did you have questions on that at all? Fantastic. Let's do it. What I want to do right now is I want to find horizontal and vertical tangents. That's the only idea I want. So horizontal and vertical tangents. Where do horizontal tangents exist? Where dy dt equals 0 or where dx dt equals 0? Where do horizontal tangents exist? That's the numerator, isn't it? So of dy dx, dy dt is the numerator. If the numerator equals 0 when the denominator does not, that means that we automatically have a horizontal tangent. So, I'm sorry, which one? Dy or dx?
Dy.
Can you find dy dt? Man, it's like piece of cake easy. There's nothing hard about this. What's dy dt? What is it? Let's try dy dt.
Minus 3.
Minus 3.
Okay. Where do horizontal tangents, you should remember this from your Calculus 1 days when you found horizontal tangents. Remember maximums and minimums, relative max, relative min? You found the derivative, right? You set it equal to what number? That's what it says. Set it equal to 0. So when dy dt equals 0, these are the points, these are the values of t for which we will get our horizontal asymptotes. Is this making sense to you? Are you guys seeing the connections?
Yeah.
Can you solve 3t squared minus 3 equals 0? Can you solve that? T equals, add 3, divide by 3, take a square root, don't forget your plus and minus, or factor the 3, do a difference of squares, 3t minus 1, t plus 1, t equals negative 1 and 1. Have I made any restrictions on the domain of my t? If I don't, that means t goes from negative infinity to infinity. You probably saw that in some of your homework. If you don't get a restriction, the domain for t is a natural domain. There's no restrictions on it by square roots or denominators, therefore our domain goes from negative infinity to infinity for t. Feel good about that one? What's the t values where we're going to have horizontal asymptotes? Negative 1 and 1. What are the points where we're going to have horizontal asymptotes? Do we know that? Could you find it?
Yeah.
Let's find it. Need some more room here. No. So, at t equals negative 1 and t equals 1, we're going to get two different points. We're going to plug in t equals negative 1 and get 1 point. That's going to be a point where we have a horizontal asymptote for a parametric equation, parametric curve. And then we're going to plug in 1. Go ahead and do that on your own while I do it on the board. So if I plug in negative 1, x is something, y is something, I'm going to get a point. When I plug in 1, x is something, y is something, I'm going to get a point. Did you do that? By the way, where do I plug in negative 1 and 1? Do I plug it in for my derivative? That'd be silly, right? It shouldn't even be 0. I plug it in for, oh, this is where I get points. When x is when t is negative 1, x is what?
1.
When t is negative 1, y is what?
2.
Okay. When t is 1, x is what? When t is 1, y is what?
No, the top one's 2.
Let's just doing what you guys say. Okay. Let's make sure. When t is negative 1, how much is y? I can get a triple check on this. Is it 2? Okay. When t is 1, y is what?
Negative 2.
Do you guys know how to do this?
Wait.
Negative 3.
Okay, let's plug in some points together.
One is-
If I plug in negative 1, this is negative 1, correct? This would be plus 3, negative 1 plus 3 is 2. Plug in 1. 1 to the third power is 1. Minus 3 is negative 2. These are correct. I just want to make sure you can actually plug in points. Welcome to pre-algebra, but that's okay. So, we have 2 points. We have 1, 2. We have 1, negative 2. Show of hands feel okay plugging in points? All right, let's move on. So here's what we know. When we graph this piece of crap, we're going to have 2 points where we have a horizontal tangent. Does that make sense? Okay. This helps us graph. This is what we're going to do to graph this problem. Otherwise, it'd be really hard. Vertical tangents. Okay, everybody, real quick, because we got to get moving on this. Where do vertical tangents happen? Where denominators equal 0. So where dx dt equals 0. You're exactly right. So we want to know dx dt. How much is dx dt?
2t squared.
Let's try that again.
2t squared.
Good. Now, when we want to find out where denominators equal to 0, we're going to take this derivative and set it equal to
0.
So let's do that. So we say, okay, yeah, set it equal to 0. This one should be a little easier for us. T equals how much? Perfect. Now, what this says is this. At t equals 0, at time 0, if you will, at time 0, we are going to have a vertical tangent this way. Does that make sense? At t equals, do we know the point? XY point. Could you find the XY point?
Yes.
Let's do that. So if I have t equals 0, that means x is going to be something, and y is going to be something, and we'll get a point. I'm begging you can answer this. What's x?
Zero.
Yeah, we're on a roll now, guys. What's y?
Zero.
Okay. Do we have a point?
0, 0.
I swear I had a point.
Yeah, 0, 0. Show of hands, feel okay with that one. These are the only horizontal and vertical tangents that exist on this problem. Do you see why? We've taken dy dt and set it equals 0. We solved for all the points. We took dx dt and set it equals 0. We solved for all the points. Now, we're going to get a little more specific. This goes into graphing like we did in your Calculus 1 class, where we know a number of things about it. We found out where we had relative maxes. We found out where we had relative mins. We found out where we had inflection points. We don't need inflection points, but we also found out x and y intercepts. Do you remember doing that? X and y intercepts. That's what we're going to do next. So we want to find the x-intercept and the y-intercept. So we had horizontal tangents. We got vertical tangents. I want x-intercepts and I want y-intercepts. Don't worry, they're not hard to find. If I have a graph, and we will be graphing this in just a moment, this is x and this is y. Where do x-intercepts happen? At what equals what? Do x-intercepts happen at x equals 0? X-intercept happens at y equals 0. So an x-intercept is going to occur when y equals 0. Do you agree with that? Every x-intercept in the world is going to happen when y equals 0. You with me? Hey, if y equals 0, do we have an expression for y in terms of t? Just set y equal to 0. What do we need to set equal to 0 here? Say it louder, I can't hear you.
TQ minus 3t.
View. That's exactly right. Do you guys see that? Man, I hope you're. This is all algebra. We're not even doing calculus anymore. But I want to make sure that you get it. Okay. Do you get that x-intercepts happen when y equals 0?
Yes.
Do you get that if y equals 0, t cubed minus 3t is going to equal to 0?
Yeah.
Can you solve that? Yes. Yes.
Yes.
If I solve this, man, well, I'm going to get t and then t squared minus 3 equals 0. Therefore, t would equal 0, t would equal the square root of 3, and t would equal the negative square root of 3. I want to make sure you're okay with those ones, are you? Okay. Well, let's try this. Do I know where, or when, do I know when, by time, of when I'm going to hit the x-axis?
Yes.
Do I know the points?
No.
No. I need to plug those in. Now, I already know it's going to be something comma 0. Do you get that? Because it's going to be on the x-axis. It's something comma 0. But I need to find the x-coordinates. So when you do this, you plug in t equals 0, t equals square root of 3. Are you getting the picture that we're always plugging in t? Always? Hey, look, honestly, look. If you have this in terms of t, and you start plotting t on the x-axis, are you going to remotely get this graph right?
No.
No, this is in x, it's not in t. You got to use your translator here to get it in terms of x. So we're going to plug in all of these things. Okay, let's do it. Plug in 0, please. How much is x when you plug in 0?
0.
Plug in square root of 3. How much is x when you plug in square root of 3 for t?
3.
Plug in negative square root of 3
Negative
for t. How much is x?
Negative 3.
Nope, do it again.
What? 30. Oh.
It's going to be 3. Wait a minute, that's weird. Do you guys see that we get the same point twice? Okay, stick with me. Am I blowing your head? I don't want to blow your heads off, okay? But here's the deal. We set y equal to 0, correct? So all of these points are our x-intercepts. We have 0, comma, well, we already showed that y is 0. That's how we got this point anyway. 0, 0. Now wait a second. This is interesting. Do you guys see that we have x equals 3 and 2 times? Do you guys see what I'm talking about?
Yes.
You guys see the 2 3s, right? We got 3, comma 0, And we have another 3 comma 0. Do I need to put it down twice? Here's what this means. This parametric equation is going to be at 0, 0 at one time. But at 3, 0, it's going to hit it once, it's going to double back, and it's going to hit it again. Does that make sense to you? That's happening. So can you get multiple x-intercepts of the same value? Yeah. Circles have them all the time. Boom, and then again, and then again, and then again, and then again. Well, this one has it twice. It's going to make a loop-to-loop. It's going to hit it once, it's going to hit it again, and it's going to go off somewhere and die, or live forever, whatever, who cares. My point is, do you understand how to find your x-intercepts here? The idea has not changed since algebra. You set your y equal to 0. Well, in terms of parametric equations, set your parameter for y equal to 0. Solve it. It's going to give you a variety of times, t's. Plug those t's in, find your x's. Since we set y equal to 0, now we have x's, okay, 0, 0, we have 3, 0, we have 3, 0 again, we don't need to put it twice. Here's what we know. We know we're going to be hitting the x-axis at 0, 0, and 3, 0. That's what we know right now. Does that make sense? We have one more thing to do, then we're going to graph it. Now, the last thing we got to do, this one's even easier, we're going to do the y-intercept. Everybody in class right now should know this. Where does y-intercepts happen? When
X equals 0.
Perfect. So if x equals 0, in our case, oh, well, wait a minute, what is our x?
T squared.
So when x equals 0, that's t squared equals 0. How much is t?
0.
Okay. I already know my x. I know my x is going to be 0. Let's find my y. If t equals 0, how much is my y?
0.
We go back up here. This is my translator. If t equals 0, y is 0. So we say, hey, I want to find my y-intercepts. X has to be 0. X has to be 0. Solve for your t values. Plug it in. We get 0, 0. Okay, on show of hands, feel okay with that so far? We're going to put everything together now. So here's what we do. Plot all the points that you have and label what they're doing. Now the y-intercepts, not really, but the asymptotes or the tangents, yeah, you want to do that. So here's what we're going to do. We're going to mark down there our x and y intercepts first. The only y-intercept we have is at 0, 0. The only x-intercept that we have besides 0, 0 is at 3, 0. Y'all so far so good. So y-intercept 0, 0, x-intercept 0, 0, and 3, 0. We have the same point twice, no big deal. Now, plot your horizontal and your vertical asymptotes. I'm going to do the vertical asymptote first because there's only one of them. Look, the vertical asymptote occurs at, go to 0, 0 and show there's a vertical asymptote that you're going to have a tangent to. So a vertical tangent is really what it is. So here, I'm sorry, was it horizontal or was it vertical? Show that you have a vertical tangent there at that point. What this is going to let you do, ladies and gentlemen, this is going to let your graph, your picture, bounce off of this and go another way, one of these ways. Does that make sense? Well, since we're over here, we're not over here. It's going to be this way. The graph's going to be over here. Now, your horizontal tangents, where do those things occur?
1 and 2.
1, 2, and 1, negative 2. So at 1, 2, we have a point, and at 1, negative 2, we have a point. Also, at those points, at 1, 2, and 1, negative 2, we have horizontal tangents. How do horizontal tangents look? Up and down or left and right? Yeah, so let's show that. We've shown the major things to graph this shape, or to graph this parametric equation. We know that it crosses, in fact, here's what we know. You ready? It crosses here, doesn't it? It's going to hit this point, it's going to hit this point, it's going to hit this point, and it's going to go back through that. That's why we had 2 of these. So somehow, this looks like this. Bounce, 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 back through. That's how that looks. Do you guys see how we get that with simply our vertical, horizontal, and intercepts? It's kind of nice. There's only one thing that we're missing. It's not a hard thing, but there's only one thing. What are we missing? Missing the direction. I know it goes either this way or it goes this way. I'm not given any t here, so we got to assume it starts at negative infinity. So here's what you do. For t equals negative infinity, you plug it in, you see where it starts. For t equals positive infinity, you plug it in, you see where it starts. So if t equals negative infinity, x and y equal, and if t equals positive infinity, x and y equal, let's try it. Plug in negative infinity for t. Take negative infinity and square it, what do you get?
Infinity.
Positive infinity. Take negative infinity and cube it. Don't worry about this, it's only leading to coefficients because that is a polynomial, so leading terms. Negative infinity, that's right. Does this graph have a place where it's at x equals positive infinity and y equals negative infinity? In fact, it's right here. This is where your start is. Now, just by doing that, you should have the direction. Is it going to go ending or is it going to go ending? Which one? Is it going to go
Second
this
way.
one or this one? So this is our end, and you can see it when you go here. X is still positive infinity, y is positive infinity. So we're starting here. We go this direction, then we go down, show it a direction for every little piece of this. Then we go this way, and we finally end up that way. That's our graph. Have I made this section make sense to you so far? Okay, the next thing we do, we're going to do some second derivatives. So it's not all that hard, a little bit harder than what we've done. I'm going to give you some formulas on how to do like length of a curve and surface area revolution, things like that next week. All right, we're going to continue our talk about calculus with parametric equations, and the next topic for us to discuss is how you would take a second derivative with a parametric equation. Last time we spent all of our time doing the derivative. Remember that? It wasn't that hard. It was just basically you do the derivative of, what one went on the numerator? Derivative of x or derivative of y?
Y.
With respect to t, and then derivative of x with respect to t, and you just make a ratio out of it, and that's the whole idea. Because they're not dependent on one another, you basically just have derivative of y over derivative of x with respect to t. That's it. Now, a second derivative is a little bit more involved, but still, it's not that hard of a concept. I'm going to prove it for you. We're going to go through the derivation of a second derivative. So here you go. Let's suppose we start with just a first derivative. Dy dx is dy dt over dx dt. This is from last time. We already know this one. So what we're going to do, because this is our equation that we proved last time, we're just going to continue with this. How do you find a second derivative? What do you do?
Take another derivative.
So let's do that. Let's take a derivative on both sides. So if I have dy dx and then dy dt over dx dt, well, yeah, we're just going to take a derivative on both. Well, now wait a minute. This is a derivative with respect to what? T, as it were. So when we do a second derivative, it's going to be with respect to t again. So we're going to have, all right, derivative with respect to t. I'm sorry, I made a mistake there. I misspoke. It's derivative with respect to x, where x is a function of t. So, and you can see it from the formula. I don't know what I was thinking. I'm sorry that I explained it that way. It is a derivative with respect to x, but because we've done it this way, the function x is also based on t. So we're gonna see two parts here. We're gonna have a second derivative with respect to x, but inherently that function of x is a function of t. So it's gonna be with respect to t. I said it wrong. I'm sorry. So we're gonna see another function of a derivative with respect to t again. So here we go. We'll start off with a derivative with respect to x. We got to match those up, and that's where the mistake came in. Derivative with respect to x on both sides. Now, if we do a derivative with respect to x on the left-hand side, this is pretty much done. This is just saying a derivative of a derivative. This is just a second derivative. Do you remember the notation for the second derivative? We get those 2's everywhere. So we're going to get a second derivative with respect to x both times. Now, on the right-hand side, we're going to do a little bit of, I call it razzle, fancy pants math. We'll do some fancy pants math over here. So here's what we're going to do. I'm going to keep this in black so you see the original. I'm going to change this into with our purple pen, so you see the changes are happening right here. What I'm going to do is I'm going to use this ratio. Remember how I can divide both the numerator and denominator by the same thing and it keeps it equal?
Mm-hmm.
So instead of d dx, I'm going to put d dt over dx dt. So I'm going to divide both by dt. You guys follow that? This is the same thing as this. Is what that is. Now, here, we'll still have in here dy dt, and we'll have dx dt. Okay, well, so we're going to have our second derivative, which we already have the left-hand side done. That's nice. On the right-hand side, what it looks like we have is, if we do this, we get d dt dx dt, and then another dy dt, and then dx dt. Show of hands, feel okay with that so far. We're actually almost done. Here's the one part that we're going to do that's a little bit interesting. Dx dt, dx dt, that's a little bit funky to work with. I don't want to have to do that. So what we're going to do to make this thing nicer, we're going to take one of these, and we're just going to multiply by the reciprocal to undo it. Does that make sense to you? We're dividing by a fraction, it's a complex fraction. Let's just multiply by the reciprocal. So what we end up getting is the second derivative here is equal to, we'll have our d dt, we'll have our dx dt, but then all of the black ones are up on the top here, the dy dt times the, if I multiply by the reciprocal, it's not dx dt anymore, what is it?
dx.
That's right. This is going to make things really nice for us, and here's why it's going to make things nice. What happens with that? Yeah, you do. These are gone, and what it gives us, you see that the reason why we don't want to stop here, we want to try to base our second derivative on our first derivative. That way we can find one derivative and then do a derivative of that again. That's basically what we want to do here. Does that make sense to you? So in our case, we go, okay, well that's pretty good. Here's what we got. We got our second derivative now. Is equal to, it says what you're going to do is do d dt of, what does this all become?
dy dx. Or
Over dx dt. Okay, we basically did some algebra to prove this, but I want to make sure that it makes sense to you. So this is basically our formula for our second derivative. Can you guys follow this all down? Show of hands if you can. Did I explain it well enough for you guys to understand it? Now, let's think about what it says. To find your second derivative, what must you first do?
Take the first derivative.
You got to find the first derivative. Are the first derivatives hard to find?
No.
No. So here's what the second derivative says. Provided you've already found your first derivative, this is why we did this, folks, is so that we could have our first derivative somewhere in there. It's why we multiply by the reciprocal, so you go, oh yeah, we're going to have a dy dx. This is our first derivative. We can find that really, really easy. Are you with me on that one? Okay, so after you found your first derivative, here's what it says. The first derivative is going to be in terms of t. Yes, no?
Mm-hmm.
So if your first derivative is in terms of t, this says, find your first derivative, just take another derivative of that. Take a derivative with respect to t of your first derivative, which is easy to find. Then, just divide it by the derivative of x with respect to t, which you will have already found. So basically, it's just one more step. You can see the similarity in finding the second derivative of what you did before.
Mm-hmm.
It's basically the same. It says, hey, just find a second derivative and divide by dx dt. That's it. Just find a second derivative and divide by dx dt. So if you feel okay with that one. Do you guys want to see an example of that?
will that mean it needs quotient rule and all that? Or?
No.
If it's a fraction, then it will. If your first derivative is a fraction, then taking a derivative with respect to t is going to involve the quotient rule. If you have t's over t's, function of t over function of t. And we're gonna study one of those right now. So here we go. So this is how we find second derivative, no problem, we proved it. Let's now use it. So I'm going to give you a parametric equation like t squared minus 4 and y equals t cubed minus 3t. And our goal right now is we're going to find the second derivative. So let's start this thing out. How are we going to find the second derivative? What do we need to do first?
Take the first
Okay, I
derivative.
want you all to do that right now on your own. Of course, I'm going to write on the board as you're doing it, but I want you to do it on your own. So recall that our first derivative with parametric equations is given right here. So our first derivative, dy dx, is given by dy dt over dx dt. Ladies and gentlemen, is this going to involve a quotient rule? Is this going to
No.
involve a quotient rule? No. This just says, hey, take the derivative of y with respect to t, take the derivative of x with respect to t, and create a ratio out of them. So what's on our numerator here? Perfect. Denominator? Show of hands if you got that. Hey, you got your first derivative right. Now, don't forget what we're doing here. What does a first derivative mean in calculus?
The slope.
Slope of a curve. What curve? A parametric curve in this case at some point. Remember doing it last time where we kept the little function and said, well, this is a slope of a point around a neighborhood for which that neighborhood is a function. Okie dokie. Now, that's our first derivative. Let's go about and find our second derivative. Here's how you do the second derivative. What you're going to do is you're just going to take a derivative of this again. That's what this part says. It says take a derivative of this thing again with respect to time. Can you take a derivative of this with respect to time? Hello, yes, no?
Yes.
Are you just going to take a derivative of the numerator over the derivative of the denominator? No, because now this is a function of t, okay? It's a function of t over function t. You got to use. So go ahead and use the quotient rule right now. So we're going to do, for our second derivative, the derivative of dy dx with respect to time. That means we're going to do the derivative with respect to t of 3t squared minus 3 all over 2t. And that's why you can see that it's going to be the quotient rule that's saying of this entire function with respect to time. Oh man, so low d high minus high d low square the bottom, and away we go. Can you double check me and make sure I get the same thing that you got? Okay.
Yes.
So let's see, looks like it's 12t squared okay, and that would be 6t squared plus 6 over 4t squared. Did you make it that far too? Just some algebra now. What should you do here? If you can, you should simplify it. Let's divide everything by 2. Okay, quick show of hands if you're okay with that one. True or false? This is our second derivative right now. No, this is just the second derivative of that function of t. If I want the second derivative of this
Divide.
function, the derivative with respect to x, well, if I want to do that, then the second derivative says this. It says you do the derivative with respect to t of dy dx, which we have just done,
Divide by dx.
and then you divide by dx dt. So here we go. The second derivative, therefore, says this. take the piece that you just worked on. So let me walk you through it one more time, okay? When you start this, of course you need a first derivative. So do the first derivative, it's pretty easy. It's dy dt over dx dt, we got it. Take a derivative of this whole piece. If it's probably going to be a quotient rule. If they both have a function of t still, it's probably going to be a quotient rule. Do a derivative again. This piece is now what's on your main numerator. It's this piece right here. So this was the derivative of dy dx with respect to t. Oh, that's this piece. We already got it. So that's going to be our 3t squared plus 3 all over 2t squared.
Divide by 2t.
And then divide by whatever dx dt was. So basically it's this. Do your derivative again, put it here, just divide it again by whatever that denominator is, because you've already done that. That is dx dt. So put this here. Does that make sense to you?
Mm-hmm.
So this piece is coming from here. This piece is coming from here. And then we simplify it if we can. So the second derivative with respect to x is equal to, whenever you have this, fraction over fraction, pretend this is over 1, it is over 1, multiply by the reciprocal, so basically you just multiply these two denominators. You're going to get 4t to the third power. Make sure I'm right on that one, 4t to the third power?
Mm-hmm.
4t to the third. And that's what we're looking for. I'd like a show of hands to see if you're okay with that one. Yes or no? Are you? Okay. At this point, we've done kind of all the hard stuff with this. We know how to graph parametric equations, right?
Yes.
Right?
Yes.
We even know how to find horizontal and vertical tangents and x and y intercepts and use that to graph, which is actually kind of cool, right? We did that last time. It makes some interesting graphs. Now we know how to find second derivatives. From here on out, I'm going to give you some applications. I told you last time, I warned you, I said this is like basically all of semester 1 calculus on parametric equations in like 2 days of lessons. So we've done derivatives, we've done how to graph, we've now done second derivatives. Next thing you did in calculus 1 is you found the length of curves, and you found like surface area revolution, things like that. And that's what we're going to do right now. So we're going to do just some formulas. I'll give you formulas for them. We might do 1 or 2 of them. I know we'll at least do 1 of them to give you an idea how you work the formula. It's not that hard. I just want to give you the formula and explain to you why these formulas are the way they are. Okie dokie. And then you can use them in formulas, just like you did in calculus 1. Okay, so from calculus 1. The length of a curve was given by this. Length was an integral from x equals a to x equals b of, you took a square root, you did 1 plus the derivative of your function, and then you squared it, and you had that with respect to x. Does that formula ring a bell at all in your memory banks? Yes, no? Have you used it in a while? No. Is it up there somewhere? I hope so. If you want to actually go practice that, the videos from Calculus 1 would be a good place to start. So go back to, I think it's, I want to say it's chapter 5, somewhere in there, chapter 5, where you do length of a curve. So that's the formula for length of a curve. The way you get that, I described that I actually proved this in that video, so if you want a proof for where that comes from, go watch that. I don't have time to do it today. You get it kind of the distance between 2 points idea, okay? Somewhat. Really, well, you gotta watch it. We make little triangles, distance there. It's like whatever. Go watch the video, okay? What we're gonna do today is I'm gonna show you how to do this with parametric equations. So, parametrically, maybe I should write this out. So that now, this was from calculus 1, so now we're going to do this parametrically. I'm going to write it out because there's some conditions that have to be satisfied here for you to do this. Here's the conditions. provided the part of the curve you are trying to find the length of, so the part of the curve for which you're trying to find the length, does not intersect itself, has no sharp points, and no gaps. Of course you can't find the length of the curve, it has a gap, okay? And sharp points is not differentiable between there, and we're going to have the derivatives just like we had here. So if you have a sharp point, it's not differentiable, that becomes a real problem. Does that make sense to you? Because you have this like vertical tangent issue, and that's a real big deal. So parametrically, as long as the curve doesn't double back on itself, where we have a problem, because we would lose the functionality there. It doesn't have to be exactly a function, but it can't double back and intersect itself. And we have no gaps or sharp points. So provided, I'll write all that out, provided the part of the curve for which you are trying to find the length is smooth. Smooth meaning no gaps, no sharp points. And does not intersect itself. Here's the length parametrically. The length of the curve, of a part of a curve, is given by a to b, a square root. Hey, that looks familiar, doesn't it? Doesn't it look familiar?
Yes.
Square root dx dt squared plus dy dt squared dt with respect to t. There's some similarities here. Check it out. You're finding a derivative of a function, right? Now this is not a function of x, but this is a function of, x is a function of t, and y is a function of t, and look at that, we're integrated with respect to t. So this still has a derivative in there, only the derivatives are kind of nice, they're easy. It says, hey, take the derivative of x with respect to t, square it. Take the derivative of y with respect to t, square it, then add them together and take the square root of it. That's basically all we're doing here. You guys understand the formula? What is a to b? Is a to b in terms of x, y, or t? What do you think? You should all know. What's this end with?
T.
Is this in terms of x, y, or t?
T.
T. That's exactly right. It's always in terms of t. If you look at it, it looks really, really, really similar to the distance between 2 points when we integrate that. That's what it looks like. It says you square the x, you square the y, you add them together, you take square root. Really similar to a distance formula, a little bit different, but it's the similarity is there. So what I'd like to do is just do a real quick example, a run through of this. I'll give you a couple more formulas that play off of this one, and then we'll call it good for our lesson. Sound good? Do you guys want to see an example of that? Okay. I'm hoping that you're finding this pretty straightforward. Are you finding this lesson fairly straightforward? It should be kind of similar because it's based on some of the ideas of Calculus 1 that we've had before, which is kind of nice. Okay, here we go. So what I want to do is I want to find the length x is given by 2t squared, and y is given by 3t to the third for our parametric equation. And what I want to do is I want to find the length on the interval of 0 to 1. Let's set it up. What am I going to have to do in order to find the length? Should I use this one?
No.
Well, is y a function of x? You know, x and y are both functions of,
T.
oh, parametric. So we're going to use that one. Let's just set this up. What do you need to know in order to set this up? Well, we have x and y. We got that. Specifically, what do I need to know inside my formula to set this up? I need dx dt, I need dy dt. So real quick, off to the side, or you can just right below this, let's find dx dt, let's find dy dt, because that's going to help our setup in just a moment. Wow, these are kind of nice to find. dx dt, what is it?
14.
dy dt, what is it?
90 squared.
Perfect, that's exactly right. What I'd like to see if you can do, I want to see if you can set up the length of our curve, for part of our curve, with this information. Go for it. See if you can just set that up correctly, okay? We'll go through the rest of it together. I'll show you some things that you'll need to know how to do here. Just some basic integral stuff. I want to make sure your setup's correct. Where does our curve start?
From 0.
Good. And because this is based on t, we don't have to change those to x's and y's. We just put in the t, so which is really nice. So we start at 0, we end at 1. We're going to have what?
Square root.
Big old square root. Okay. What's inside the square root?
4t squared.
Sure, it says take dx dt, and don't forget to square it. You got to have square. What's between there?
Plus
And then you have
90 squared squared.
squared.
Sounds funny. Squared squared.
Squared, squared. Squared, squared. Roger, Roger. And then, now what? Oh, let me ask you an algebra question, because this would be really cool. Does a square root just get rid of that square and get rid of that square and we're good to
No.
go? Please don't ever freaking do that. If that was the case, would you even have this formula? No. It'd just be, hey, add them together. That doesn't happen, all right? Some of you algebra freaks out there that don't like to do whatever. Anyway, I graded your tests. Oh, algebra, goodness. Okay, so we'll continue. 0 to 1, big square root, simplify it. What do you got there?
16t squared.
And t to the 4th dt. Oh my gosh. What's some idea? I want some ideas. What would you do? Is a substitution a good idea?
No.
Would I want to jump straight to a trig sub or something?
No.
Give me an idea then.
Factor out t squared? Yeah.
Factor out the t squared. That's a pretty good idea. And here's why it's a good idea. If I factor out the t squared, then I get 0 to 1. I get square root of t squared times the quantity 16 plus 81 t squared dt. Right side people, just you guys. Tell me why this is going to be useful for me to factor out that t squared. Say what now?
You can just suck the t squared out?
I can. Remember that square roots are separable by products, and since I have a product right here, after I factor this, I can't separate addition. I can't do that. It's impossible. Well, what I can do is separate products. So the square root of t squared is simply, so that we have 0 to 1 of t square root of 16 plus 81 t squared dt. Oh, do you see it? It's beautiful. It's not a hard one. It's an easy one. Why is it an easy one? What are you going to do there? Come on, everybody should know. Everybody. Say what? U sub. Just do a U sub. Trig sub? No, that's crazy. Is the derivative of this thing somewhere in your integral being multiplied? Then do a substitution. Use this as your u and do a substitution. I would also like for you to change bounds in this example so you don't forget to plug back in your t, okay? So change bounds on that. That way you can leave it in terms of your u instead of having to go back to your t. Does that make sense? Okay. So go for it. I'm going to erase this side of the board. I want to give you some time to do that on your own. See if you can make it all the way down. Let's see. U equals 16 plus 81 t squared. 1, or sorry, when t equals 1, u equals, and when t equals 0, u equals. I'm going to pause you for a second. Do y'all remember how to change bounds when you do this? You use your substitution and you just plug in the variable that you don't want anymore. So I have t's, I want u's. So change your bounds. If I plug in t equals 1, I just plug it in here. If t equals 1, then u equals how much?
87.
How much?
97.
97. So u is now 97. Okay, very good. Now, if t equals 0, how much is u?
16.
Probably 0. So now we're going to have some new bounds in terms of u, where when we evaluate this thing, we don't have to plug back in our function of t. Does that make sense to you? Are you guys with me? It's old news, but we haven't done it in a long time. Well, now our integration by substitution shouldn't be that hard. We should get 162
T,
T.
dt.
dt. If I divide by 162, I get du over 162 equals t dt. Hey, look at that. Is there a t dt somewhere in your existing integral?
Yes.
It's right here. So we're going to take this and say t dt? We want du over 162, and that'll be our substitution. So I'm going to change it up. I'm going to put it right here. Can you please tell me, everybody, where does my new integral go from, please?
16 to 97.
Perfect. We changed bounds. What are these in terms of, t's or u's?
U's.
Very good. That means everything else has to be in terms of u. What do I have now? Square root. Very good. What happened to my t? That's part of my du over 162. So t dt, du over 162. So square root, what's inside my square root? U.
U.
And then I get du over 162. So let's make sure we got this right. This piece became our u, so we get square root u. Our t dt becomes du over 162. We got it. Our bounds have changed to 16 to 97. Got that too. What now do you do?
Pull out the
162.
Yeah, that's a good idea. So we're going to go 16 to 97. Also, I'm probably going to change that. How am I going to change it? Okay. So now when we do our integral, we have 1 over 162. We've got, what's the integral of u to the 1/2? We should all know that. What is it? U to the 3/2, because we add 1 to it. So u to the 3/2 over 3/2. You always add 1 to your exponent, divide by the new exponent. Do we need a plus c? Yes, no? No, for definite integrals. Now, we'll do some simplification here. The 2 moves to the numerator, so we have 2u to the 3/2 all over 162 times 3. What now?
Simplify.
Probably simplify it first, because 2 over 162, we can simplify that back down to 81. And then 81 times 3,
243.
I think so, 243. Isn't it?
243.
243? It'd be the same thing as 3 to the 5th, so u to the 3/2 over 243?
Yeah.
Perfect, okay. Now what? Would you, okay, here's my question. Would you plug back in your function of t right now?
No.
Pretend you hadn't changed bounds. Would you plug in your function of t right now?
No.
If you had not changed
Oh,
bounds?
Yes.
Yeah.
Yes.
Would you plug in your function of t right now?
Yes.
And you'd go from 0 to 1. You with me? Here, we changed bounds already, so we don't have to plug back in our t. We're just going to go from 16 to 97. So we plug that in, we go, okay, the length of our curve is going to be exactly this. We're going to have 97 to the 3/2 over 243 minus 16 to the 3/2 over 243. Or you could even do the subtraction and multiply by 1 over 243 if you wanted to factor out that fraction. Now we're going to approximate here with a decimal. So this would, by the way, this would be exact. If you want to simplify these two things, that would be an exact answer. If they ask for an approximation, then use your calculator. Has anyone done that? Taken 97 to the 3/2 power, then divided by 243 and done the same thing with the 16?
3.67.
I think you're right, 3.67. Whoever said that? Is it you? I've always found it really, and it's rounded, correct? I've always found it really interesting that you can find the length of a curve without even knowing what it looks like. So we say if you were to graph that, if you were to graph that parametric equation and say, I want you to find the length from 0 to 1. The length from t equals 0 to t equals 1 is 3.67, which says, well, that's kind of cool because this really maps an object, right? So if you had this as a map of some sort of object and you want to find out based on time how far it went in 1 second, you could do it. That object went 3.67 units in 1 second. It's an interesting idea. Show of hands if you feel okay with the idea. Can you do it on your own if I just gave you the formula? Okay. Now the next, there were head nods. Okay, I saw some head nods. Like, you better be able to. I mean, can you take a derivative of t and a derivative of t? You gave me the when I asked my dog. Yeah, exactly. You can do our derivatives, square them, just plug in the formula. Okay, don't forget to change bounds. It's basic calculus 1 after this point. It's basic calculus. Now, the last thing. Let's see. Do you guys have any questions on this stuff at all? Because I'm going to erase everything but like this little part. I like these integrals. I'm going to give you a formula. We're not going to do any examples. I'm just going to show it out there because it's very similar to what you've done here, okay? If you're asked to find the area of a surface of revolution, here you go. Do you remember these areas of, well, surface of revolution for an object? So if you have like some sort of function that says revolve this around the x-axis, well, it's going to do something like this. It says now, since that's three-dimensional, I want you to find the surface area, how much gift wrap it would take to wrap this thing up, excluding the ends. That's the whole idea. Or saran wrap is more flexible. How much it would take. So that's the whole plan. This is what we're doing. But there was two formulas. There was one for the x-axis and there was one for the y-axis. So what I'm going to do is I'm going to give you the old formulas from Calculus 1. I'm going to show you how they relate to the new formulas for parametric equations. You with me? So we'll do around the x first. And then around the y. From Calculus 1, here's what we did. We went from a to b. We had 2 pi times f of x, and then we did this. And this should look real familiar. This is why I had this on the board at the beginning of class today. This is how revolving around the x-axis works. And here's why it works. If your Calculus 1 teacher didn't say this, I know if it was me, I said it. It's on the video. I prove it. Here it is. Here's what it says. It says if you integrate 2 pi, if you're around the x-axis, check this out. If you're going around the x-axis, your radius is actually the height of your function. Do you see it? It's f of x. So this is 2 pi r. This is the circumference of a circle. That's all. That's what the cross section is here. It's the circumference of a circle. And then you integrate the circumference of the circle for the length of the curve. That's the length of the curve. So basically it says circumference, 2 pi r, times length. That's all it says. Now does that make sense to you?
Yeah.
That's the whole idea. Well, if we want to change that, here's how it looks parametrically. We go from a to b, but now it's in terms of t. we have 2 pi. Now listen carefully. Do you understand that f of x can be given by y if we have a function? If we have that, well then f of x, that's the height, that's basically just saying the y direction. You get it? So then f of x just changes to y. That's pretty easy. That's going to be in terms of t. Are you with me? And then we'll have, well, if this said 2 pi, that says 2 pi, those are constants. That said f of x, that says the height, or y in this case. If this says the length of a curve, then we're going to have the same thing we had here, the length of a curve. Dx dt squared plus dy dt squared with respect to t. That's the whole thing. I just wanted you to see where the pieces come from, that it's not just magic, all right? The idea is, if this is going to be the surface area of revolution around the x-axis, the radius will be given by the height, which would be in terms of y. This is circumference, cross-section, so a circle. This is length of the curve and what you're integrating. Show of hands feel okay with the idea of this thing. Now, in order to do this, look at, this will be in terms of t, right? This will be in terms of t, right? You can't just leave that a y. What are you going to do?
You put bar in T.
You're going to take whatever that is, the y, and you're going to put it there. And then you work on it. So it's all got to be in terms of t. That's why we have a dt over here. The other one, I'm just going to state it. It's really similar. You can probably see the changes that are going to happen. If this were around the y-axis, that'll be g of y. This will be g prime of y. This will be x. This will not change. So let's see. We have integral a to b now in terms of t. 2 pi still gives us our radius. Look at, if we're going around the y-axis, if we're going this way around the y-axis, then our radius would now be x. G of y would be, oh yeah, x. I'd still have a square root. It's still going to be the same length. Length of a curve, that's really interesting, right? Because length of curve depended for functions on whether it was a function of x or a function of y. For a parametric, it doesn't, because they're not a function of each other. They're just functions of t. So length of a curve doesn't change no matter what way you're revolving. Isn't that kind of interesting? Because the length is just the length. Whether you're going right down, you can go all around if you want to. It's just the length of the curve. That's kind of cool parametrically. So here we go. Dx dt squared plus dy dt squared dt.
And the line still has to be smooth.
Yeah. Yeah. Well, and the reason it has to be smooth is because you're taking derivatives of it, right? If you have some awkward points, you're going to have one of these things that's undefined. That would be an issue. So just use the formulas. Again, if you're going around the y-axis, your radius would be an x value. That's where this is coming from. It's just the circumference of all these circles, and you're integrating across the length of it. Did you understand why the length does not change whether we're going in terms of the x or in terms of the y? Did you get that? With functions, when we had our functions like this one, well, it depended because y was dependent on x or x was dependent on y. So when we have them in terms of one function, you have to relate it as such. When we have both x and y in terms of a different variable like t, it doesn't matter because they're just relating to time instead of actual x or y axis. And that's why we don't need to change this formula at all. Show of hands feel okay with the idea. Do you think that you could find dx dt and plug it in? Do you think you could find dy dt and plug it in? Do you know how to square things? Do you know how to add things?
Yes.
And take square roots?
Yes.
Okay. And do you think that you could take x and plug it in there if you're going around the y-axis? And you know how to do integrals, right? That's what most of this class is all about. So after that, it's just using the formula. And if you need help with that, you can come in and see me.